Hey guys, in this video I want to talk about the difference between how and why. Now obviously they are very different questions and both of them are very important questions as well, and that is what makes this question very important and very interesting. And the question is which is more important? Which question, I mean which approach is more important, the why approach or the how approach? And I'll tell you what I exactly mean by that. Now, basically, before I begin to talk about my personal views, let me talk about what's objectively accepted, and that is obviously true, and that is that both how and why are equally important. We cannot simply ignore one approach completely and just follow the other one, and then we cannot expect to to work out. But still, I thought it would be interesting to discuss maybe which of them not just uh, like kind of have a fight between them, put them against each other, but rather just to discuss the difference between them, and then that might and share some insights, my personal insights obviously, but then that might help you figure out your own personal favorite, or let's say your own the approach that aligns with your interests in life, because that is something which is entirely your personal choice, your subjective choice, right? So, if I put it in very simple terms, the why is more the philosopher's approach, and the how is more the scientist's approach. Although it's a very crude way to say it. It's not really like, don't take it at face value, okay? Because scientists are also all the time. Why is also a very important part of science, and why is the starting point of science. Now, if we talk about the starting point of science, well, that was again philosophy. Philosophy and science separated out only much later. But if we look at human history, I mean, even before Newton and Galileo and stuff, there was something called natural philosophy, which was the study of nature around us, and that is what developed into physics and science. So basically, in the very old early days, not much difference between science and philosophy, because the question then, I mean, the motive or the ultimate goal was to understand the world around us. So that is why does this happen, why does this happen this way and not that way? Because back then we didn't have this kind of technologies and the issues that we're dealing with today. Like, if you don't have an airplane, then you would need no field called aeronautical engineering. You don't need to spend so much time trying to figure out how to make planes fly better or in a more efficient way if you don't even have airplanes. So there was no technology at all back then. So people didn't have to worry so much about how, because what is there to worry about? I mean, first of all, let's figure out why the world is the way it is, and then that. So that is how it began actually. But then studying why, that gave rise to a lot of important technologies, and that made life easier, or in some ways that changed the way we live, that gave rise to a lot of new technologies, new revolutions, new industries. And then the focus, I think, shifted from why to how in the science. And even today, as you can see, there is a lot of thrust on applied sciences, interdisciplinary sciences, which is good thing, because the problems that face us today, climate change, I tell this in every video, so let's not repeat it, but these problems are very multifaceted problems, and to solve these problems you need people from different domains of science. It's not simply a question of philosophizing that why does this happen, why does this happen, and writing some equations. It's not that kind of problem. You need to understand how the system behaves first, more importantly than why, and then you need to model it. You need to connect the dots from different branches, and then you need to give a solution that works. Whether we understand it is secondary, but whether it works is primary. Understanding is more has more to do with philosophers, because in today's world there is a very great divide between science and philosophy, which is good in some ways, because philosophy can often have the unintentional effect of misguiding science. But again, it also has its problems, because I think philosophy can do the job, can play the role. If utilized in the correct way, philosophy can play the role of bridging the gap between the different branches of science, which is again very important in today's world. So yeah, now let's talk about a very important example is modeling. So whenever you're trying to model some phenomena, some complex system that you see in the world around you, what you do is you start with maybe you start with a mathematical model, you start with a nonlinear equation, maybe, or any kind of equation. Basically, let's say a differential equation or a difference equation, whatever. So basically, when you are writing the equation, or when you are kind of building the equation, if it's a new model, and if it's already an existing model, maybe you try to modify the equations. Either way, your motivation is to understand how the system works, and more precisely, you want to understand, you want to build a model that will reproduce the behavior of the original system, right? But these are all models. That's why we say the word model. Model means it's not original. It only does, it only gives you a model. But the question that you ask is how to build a model so that it will reproduce the behavior of the original system. That is your primary concern. Now, if it works out, it is a very difficult job anyway. I'm not trying to undermine that this job. I'm not saying that how is useless and why is useful. Both are useful. But if you succeed in building a very successful model, then in the future you will ask why the system behaves that way. Then you, because you cannot study the system, the original system in nature. In many cases it's a very complex system. So first is you build a model. You ask how can I build a model so that it will reproduce the behavior of the original system. Now once you have a good model, even then you should always keep in mind that this is nothing more than a model. So maybe just maybe some little intricacies or some little nuances of the system could be present that are not being reflected in the model, because it's only a model. No matter how accurate it is, if you maybe study the system for a very long period of time, let's say 1 million years, just for the sake of argument, you may see that there are some aspects, you might see some nuances in the original system which your model will not incorporate, because you've just built a model by looking at the system for a short period of time, on the cosmic scale, a very short period of time, and based on some past knowledge and observations, much of which might also depend on assumption, depending on the model you're building, the kind of model, the kind of system you're working on. But yeah, so first question is how, and once you have figured out that how to build a model that reproduces the behavior, you have a working model. So you have a very good, maybe it's a very good model, very accurate model, but it's still a model. So it will only model the behavior of the original system, but it is not the original system in its full, in its entirety. But then, but still, if you have a very good working model, then often you can move on to why, and then you can ask why the system behaves that way. Okay, so I cannot study the system, but I have a model, so let me study the model in order to understand why the real system behaves that way. So by study the model, you can change, you can just tweak the parameters and see what happens. You can change the values and that. Basically, kind of like trial and error. You can, but yeah, not only trial and error, but yeah. So that is the thing about that's the how. I mean, modeling is an example. In modeling, the main question is how, not why. But not just modeling. In many sciences, in many industries, we are more interested in learning, in figuring out the how. For instance, even us, like, we are not computer scientists. I mean, I am not, at least, and most of my viewers probably are not. If you are, this is not for you. This particular part of the video is not for you. But yeah, the guys who are not computer scientists, and when they see a laptop, when they, let's say they buy a laptop or they download a software, their target is not to understand why the software works or why this software. I mean, they're more interested in just asking how to use it, how to use this software, how to use this device for my benefit. You buy a new electronic device, you will read the manual, and you will be interested in how to use the device. You will not ask, why does this device work? Oh, why does this device work? Let me just open the device and let me see each and every circuitry inside, and let's see, why does this work? Wow, this is amazing. I mean, that is the job of the ones who are building the device, not the ones who are using the device. So same case in science also, it's much like that. So the guys, many scientists, I think the majority probably are more interested in how than why. The why only comes as a maybe in the future, or maybe in most papers as a discussion or something in near the end. Yeah, philosophers on the other hand, or even in some cases mathematicians, they are more interested in how. Mathematicians is a very kind of dangerous example to give, because it depends really on the context. But yeah, in some way, yes, I feel at least, because there is something called counterfactuals. You may have heard of it, counterfactuals, and it actually it's an idea that originated in mathematics, but it's used a lot by physicists and guys who model complex systems. So basically, counterfactual means the study of something or some phenomena or some idea or some fact or some object, whatever, that is not true in our world. I mean, that is kind of impossible in our world, but the counterfactual, the guys who are doing counterfactuals, they ask a question like, what if this was true, then what would have been different? As a simple example, let's consider two possibilities. One is, today is a very sunny day here, as you can see outside. And let's consider possibility 2, that is the second possibility, that it's a very rainy day, like no sun, it's very rainy, overcast, cloudy day. Now both of these possibilities are true in our world. They are possible in this world. I mean, yeah, right now it's sunny, but we also know that this might be cloudy. This will be cloudy sometime in the future, definitely. And this has been cloudy many days in the past. So we also have some evidence. So this is true in our world, right? Cloudy and sunny both are possible in our world. Yeah, right now it's sunny, but that's a different thing. So these are possibilities that are true in our world. But counterfactually, let's not give you, let me give you a kind of let's say crazy example, but just to give you an idea. Let's say the sun, let's say the sky becomes green, and the trees you can see, they become blue. Now this is not possible in our world, right? We due to a lot of reasons, because the sky is not a thing. It's just the vast expanse of space, and blue light has the smallest wavelength, and that means it has the highest frequency, the highest energy. So why is the sky blue? Most of the time we know that because the the light see, we can see the sky and everything because of the light from the sun, and by the time the light from the sun reaches us, because the sun is very far, pretty far away, so our eyes cannot see the blue light. This is a very like high school level explanation, and this is true. I mean, if you know, you just need to learn about light scattering, Rayleigh scattering, and all this scattering. The red light gets scattered and this and that. So the blue light is just light scattering is all you need to know to explain. So we know why the sky is blue. We also have a very pretty good idea why the trees are green, because of chlorophylls, pigments, the color of them. I don't know the technical details, but yeah, it's not like these are not really mysteries. We, of course, we don't know everything about trees and skies, but we do have a basic idea why trees are green and why the sky is blue, and why the sky is not green, because yeah, again we have that explanation. See, and in different, it's kind of strange, but under different conditions, you can see a sky that is, black, like not exactly black, but very dark, cloudy. You can even see during sunsets and sunrises, you can see a reddish sky, reddish, pinkish, yellowish. All of this is possible, but green is a color I think you'll never see it on the sky. So this possibility that a green sky and a blue trees, I don't know. There are so many trees in, maybe in some distant forest, or in somewhere maybe there's a tree with blue leaves. That is, I mean, of course there are blue flowers, but an entire tree that is blue in color, even that could be possible. I don't know. Just try to give an example. But yeah, so green sky is a counterfactual, because it would never be possible in our world. We don't see, so it's not possible. It's not just that today the sky is blue, but tomorrow it could be green. It's not that kind of thing. It's not possible at all in the real world. In the world of counterfactuals, well, there is nothing called impossible. Everything is possible. Basically, you can think of it like this. It's just a combination of particulars and properties. So instead of describing an object like sky and just assuming it to be blue, let's say that sky is an object. So sky is a particular. Tree is a particular. So these are particulars. By particulars, I simply mean some object which can be, and when we talk about particulars and properties, usually we try to define the objects just by what they are, not by their properties. So in this view, the blue color is a property of the sky. It is not the sky itself. So the sky is a particular, and the color of blue is a property. The sky is blue. The color of green is a property. Every color is a property in that sense, because color is not something you can see. I mean, you cannot see that this is blue color. You can say that, okay, this sky is blue, so that is a manifestation of blue color. The tree is green, but if I ask you what does blue color look like not the, like that is blue, you can see that what blue looks like, not that. I mean, the notion of color, this blue, it doesn't exist physically. You cannot hold the color blue. You can hold an object that is blue in color, but you cannot hold the color blue. I hope you understand what I'm trying to say. So these are all particulars: trees, skies, buildings, whatever, and these are all properties: blue, green, whatever. So the combination of the property green and the object tree exists in our world. You can see green trees, and for the combination of the property blue and the particular sky also exists in our world. But the combination of the property green and the object sky does not exist in our world. So that's why we don't see a green sky. But in the land of counterfactuals, it's all possible. So basically what we are interested in doing in counterfactuals is that we try to model, because when we're doing simulations, when we're doing modeling in the computer, we are not under any constraints. The guys who do experiments, like real experiments on a real physical system in the laboratory, they have to take care of a lot of things, because their job is a little more difficult. They have to take care of the real physical constants, because they're working on a real system. They have to ensure what is I mean, they have to take care of the constraints pretty well, otherwise they cannot get an accurate results. The guys who are doing modeling or simulations in the computer, they can simulate a green sky, nobody's preventing them, and just to see what happens. So green sky was a very silly example, but just an example. But in reality, counterfactuals is important, because people often do this. Let's say you're studying a model for the weather. Let's say the usual, you have the Lorentz attractor and stuff, or some other model as well. So you're trying to study weather prediction and stuff. So just to better understand a model, just to better understand why this model works this way, Often a very good approach is to ask how would this model have behaved, or how would this system have behaved if it was different. Maybe this difference is something, maybe such a system does not exist in the real world, but you can just model it. You can just model a system by changing the parameters in such a way that it does not exist in real world, much like the green sky, but you can study the system. So yeah, if you actually study, if you just this is a very silly example again, but just to give you the idea. So if you simulate a green sky and then study its properties, maybe you can understand why in the real world, like in our world, which is subject to a lot of constraints, the laws of physics and stuff, why a green sky is not possible. So often understanding why something is true is a good way to understand that, is to model something that is not true, similar system but with different properties which are not true, and then try to figure out why those are not true. It's kind of just like the method of exclusion. Once you have figured out why that, let's say there are three possibilities, if you can explain why possibility 1 and possibility 3 cannot be true, then you automatically explain why possibility 2 has to be the case, right? Yeah, and there was a famous quote by Sherlock Holmes that whenever you have eliminated the impossible, then whatever remains, however improbable, must be the truth. Simple, yet often overlooked, as Sherlock Holmes used to say. So that's the thing about counterfactuals. Yeah, so basically how and why, that is the point of this video. I kind of lost track in the middle. So counterfactuals are basically asking, counterfactuals is I think a bit more closer to why than how, because when you're just studying counterfactuals, you're no longer interested in how. If you only ask how to build a model that can mimic the behavior of the system, you don't need counterfactuals. You just need to observe the system that is present in the real world and try to model its behavior using whatever software, simulations, computation. That's all. You are not asking why. But if you want to ask why this system behaves this way, maybe you study a system that is different from this system, same framework, but some differences such that such a system does not work, does not exist in the real world, but you study it. And that might give you some good insights into why that's not true, and then you automatically understand, you at least you get some insights like why this system behaves this way. So that's more closer to why, not how. So yeah, I think I gave you some, maybe in a very incoherent way, but still I gave you some idea about how and why. Now I would have to end this video on a very, like, okay, so ultimately the question would, you might already have this question in your mind. So just for fun, of course, I understand like both how and why are important in the pursuit of knowledge, pursuit of truth in scientific research. But still, if I had to choose one, or if you had to choose one, is there any kind of like how versus why kind of thing? Again, that's not really possible, as I told you, both are important. But still, personally, I think uh, maybe how is a little more important from the point of view of, the immediate problems, immediate challenges that humanity is facing. So if you want to find a cure for cancer, you need to understand how the proteins and the viruses behave that way. And if you understand the how, then it would be a very simple, maybe not simple, but still it would be possible to build a machinery, build a drug or something. I'm not an expert on this, so please don't, maybe I'm not speaking very accurately right now when I'm talking about the cancer part. But if you could model these things, and if you could understand exactly how these viruses work, or how the cancer cells, the proteins in the cancer cells or whatever, they behave this way, this protein folding and all this stuff like that, if you can understand the mechanism behind it, mechanism means how, not really why, then I think that knowledge would be sufficient to take us a long way forward in cancer research, in finding a cure for cancer, maybe even if you're lucky. But why? It's much more fundamental. So we don't really need that to build medicines or to model real world systems to predict the weather, or to a lot of applications, even to battle climate change stuff. Why is not really required at that. Of course it's required, but how is more important, more dominant than why. That's what I'm saying. Maybe 90% is how and 10% is why, or something like that. Maybe that is the point. Why is more, I think, so yeah, how is more important from that point of view. And also, if you are more interested in the how, that means if you have a lot of experience in working on the how, that means simulations, modeling and stuff, working across various disciplines, then from your personal point of view, you also have a very good like much better career prospects. But if you're more interested in the why, maybe you just philosophize all day long, you write philosophy articles, or maybe even science articles, but they're very theoretical, very abstract, then definitely there is a problem of research funding all over the world, and no point like acting it, there isn't. So there is a problem. And yeah, but I'm sorry, just slipped. But I think the why is very important personally, because the why could act like a fuel in your career, or in your I mean, it could act like a motivation. At least in my case it does. Let me quickly say why. I mean, let me explain why I think why could be a motivation. right? The second why is within the quotations. And with that, I'll just that would be all for this video. Yeah. So I think, see, why gives you a space that is only yours? Because if you just go deep in through why, just go deep means, I'm not saying you take a lot of courses, you learn a lot of textbooks and do a lot of research on this, because this is something for how you need some formal training. Like formal training means the usual training, because if you are in a good university, if you're in a good course, if you're under a good supervisor, and if you are hardworking, anybody, whether they're extraordinary or just ordinary, anybody can master the tools, master the how to do a simulation, how to model stuff. Maybe it's not very easy, but it's doable. But why, if you go, why, the beautiful thing and maybe the dangerous thing about why is that if two different people walk down the road of why, maybe, just maybe, they might reach very different conclusions. And this is something very personal. Why can help you develop a personal philosophy of the world, and no textbook, no university, no course can help you do that. It's something which is entirely your own. So the dangerous part of this is that is why the theories that are very abstract or theoretical, I mean, that are more towards the side of why, most often they are not, that they cannot be verified by experiments, and they're often not even scientific, they're more towards the philosophy side. That's a bad thing. But yeah, personally, why can be a motivation for you, because why can create a space, why can help you create your own philosophy of the universe. That need not be like any standard I mean, just your way of looking at the world. It should not contradict any scientific view, but it should not be just any known theory as well. It's not a theory of everything or that kind of thing. Just your way of viewing the world, not just about science, but also beyond science in life. So it can, at least in my case, it has. I'm not sure how general this claim is, but I think why can help you build your own philosophy of the world, and that is something which is entirely your own. And you will need, we all humans at times, we need a space that is entirely our own, because especially there is so much negativity in today's world, so much toxicity in today's world, especially the people all the time they claim that I am there, that they're doing something different, while in the true sense they're just following the convention, they're just taking the safer road. And yeah, so this is of course the convention is shifting. Few years back convention was different, today also the convention is shifted, but people are still following that convention, the shifting convention, but they're still following the tradition, the convention. They're not doing something new. So your path should evolve in a much faster than the evolution or the shifting of convention. Only then you can claim that I'm doing something unconventional or unorthodox, something new, something different. Otherwise you cannot really make that claim. I mean, the point is, in today's world, there is so much toxicity, so much negativity. I think we will often need need a space that is entirely our own, and I think philosophy can help us there. I mean, especially asking why, because why does this happen? Science cannot give us an answer in many cases, because if it's a very deep why. But you can maybe find a philosophy. You can try to connect the dots. Whether it's true or not, you never know, because these are often the kind of questions that cannot be, that you carry out experiment or do a simulation and do just maths and values, and you can tell whether it's a correct hypothesis or a wrong hypothesis. It's not that simple always. But yeah, that's the reason I think why is also very important. So I hope you enjoyed the video, guys, and this video just a very kind of interesting video in which I outline the differences, the pros and cons of both the how and the why approach. But I think at the end of the day, if you want to be successful in whatever you do, you need a combination of both. So yeah, thanks for watching.